Good greetings to all. I'm Rohan Tiwari from class A5, B1 batch, roll number 11, and my topic is Eigenvalues, Eigenvectors, and special matrices. That we have an introduction of special matrices, Eigenvectors, and Eigenmatrix. Here we start. Here in the slide, we can see that the presentation of eigenvalues and vectors have two types of special matrices that are Hermitian and Unitary matrices. The concepts in this are first that we can be fundamental in many quantum mechanics, signal processing, and machine learning. We will define the concept in many more discussions of the key properties. Here we start. Here first, eigenvalues. What is eigenvectors? Its definitions. What are the eigenvalues? Here we describe that eigenvalues are the number such that when a matrix or multiplies a vector, the result is just a scale version. For example, that here we see in the slide a v equals to lambda v. In such a word, the scalar describes how the eigenvector changes under linear transformation. As for to find the eigenvalues of a, like we can assume we have to find a. Then we have to solve the equation a minus lambda I equals to 0. Here I is identity matrix. We can shift to now eigenvectors. What are the eigenvectors? Eigenvectors denoted by V corresponding to eigenvalues lambda. Here lambda is eigenvalue and V is eigenvectors. So when multiply a matrix A, the eigenvector only changes by a scalar factor, the eigenvalue, retaining its direction. Here we go. Eigenvector associated with distinct eigenvalues is the independent and crucial property. For the next part, want to see what are the examples of that. First, we see matrix definition. If you consider A matrix 2, 1, 1, 2, and we have to find its eigenvalues. So what we have to do? First, we have to find a determinant. Determinant, then determinant A minus lambda I. We can see lambda equals to eigenvalues and I equals to unitary matrix. I equals to unitary matrix. So equals to 0. And then we find a characteristic equation for the determinant. Yeah. Then we going to find eigenvalues. Then we can jump to eigenvectors. For like you have consider eigenvalues, then we can find it eigenvectors. See, if you can give a like in this see in this PPT, we can find lambda. Lambda values means eigenvectors. First we have to find eigenvalues, then we have to find eigenvectors. For the further process, we have to check now Hermitian matrices. What are Hermitian matrices? First of all, I want to tell you that uh, we have to we can find the eigenvalues, eigenvectors in quantum mechanics by the app Wolfram Mathematica. See you in later. First, we can see Hermitian matrix. What are Hermitian matrix? Hermitian matrix is a complex square matrix that is equals to its own conjugate transpose. That is A equals to A transpose. Like A equals to A transpose. Key properties are the diagonal elements are same. Off diagonal elements are complex conjugates. And eigenvalues are equal and real. For example, if you consider A 3, comma 2 plus iota and second 2 minus iota comma 1. Since A equals to A transpose, its eigenvalues are approximately 4.62 or minus 0.62 as a real number. For the real diagonal elements, the elements along the main diagonal of a Hermitian matrix are always real numbers. Conjugate symmetry, elements located symmetrically with respect to main diagonals are complex conjugates. Here we see eigenvalues. Eigenvalues of a Hermitian matrix are always in real numbers. For the further, here is example. Matrix example as 3 plus 2 iota in 2 minus iota comma 1. Then we have to find it conjugate transpose. The conjugate transpose is 3 comma 2 plus iota 2 minus iota 1. which is equal to A. Therefore, A is Hermitian. Means if you give A, then we have to find its conjugate. Then its examples are the eigenvalues A are real and fundamental. Then and further, we find unitary matrix definition. Unitary matrix is a complex square matrix U such that conjugate transpose is also inverse. That for equal U transpose U equals to U transpose. First we have U, then its transpose. So U transpose equals to U transpose U equals to I. Identity matrix. Its properties are the following properties: columns and rows from the orthogonal basis. Determinant has absolute value 1. Important in quantum mechanics is that unitary matrix represent transformation that conserve probability, the crucial aspect of quantum mechanics and systems. Its key properties as following: the columns and rows of unitary matrix form an orthogonal. Determinant of orthogonal equals to 1. Unitary matrix example. Matrix example. Consider U unitary matrix, then 1 comma 1 by root 2 comma 1 by root 2 minus 1 by root 2 1 by root 2 conjugate transpose. First we have to give it transpose, then normal. The conjugate transpose UT is 1 by root 2 comma 1 by root 2. Product calculation means we have to find its calculation, then we have give product. Importance and implications of that. In for the things, we can see what is importance of this. We can find this eigenvalues, eigenvectors, Hermitian matrix, unitary matrix in quantum mechanics by the following app Wolfram Mathematica. Here we see later. Second is signal processing. Eigenvalues and eigenvectors are used in spectral analysis and filter design. So for the following, data science. Principal component analysis uses eigenvectors to reduce dimensionality. Operations involving eigenvalues and eigenvectors. Diagonalization, power iteration, single value decomposition, UR algorithm. For the first, diagonalization. A matrix can be diagonalized if it has n linearly independent eigenvectors. First, we think diagonalization. We can understand by that the thing matrix can be diagonalized if linearly independent is the main process. So linearly dependent would be better. Eigenvectors, okay. Power iteration, an iterative method to find the dominant eigenvalues and corresponding eigenvector. Single value decomposition, SVD, the generalization of eigenvalue decomposition for non-square matrix. Last is QR algorithm, an iterative algorithm for linearly eigenvalues of a matrix. Key takeaways, normal and further exploration. We can explore that. First of all, we can think, I have tell you the quantum mechanics we can do in Wolfram Mathematica. So I have solved some examples. First, to find the eigenvalues, eigenvectors of given matrix. A equals to 4, comma, minus 1. Eigenvectors. Eigenvalue equals to eigenvalues A. We have take the matrix A. Eigenvectors equals to eigenvectors A. We have take the matrix A. So this gives us the output. Second, eigenvectors equals to eigenvectors 1. We give the values as 1. A equals to 1 for the following process. We can also prove some various processes as A equals to CV, ACAV. So, like that. To verify the properties of inner product. If A is Hermitian matrix, then for all V, what are the Hermitian matrix we have studied? A equals to A transpose. The matrix equals to matrix transpose itself. To a Hermitian matrix, then for all V, V1 belonging to complex vector space we have. Then we can, following input, we can get the best output. So for the further, V1 equals to matrix, then R equals to dot conjugate transpose dot A comma V V1 dot conjugate transpose V conjugate transpose A V1 R3 dot conjugate transpose V dot A comma V1. As we have seen the complex numbers, you can also try that. For this, you have to download Wolfram Mathematica. And so by seeing the what is unitary matrix are preserved inner product, that is U is unitary, then for all V comma V1 belonging to complex vector space of dimension we have. So see, U is unitary matrix, U comma V, U dot V1. We have to make this process by doing dot conjugate transpose. And dot by doing this conjugate we have to take, as we have studied Hermitian matrix, unitary matrix, eigenvalues, what are eigenvectors. For us given matrix, you can find it by giving characteristic equation. Then as we are doing recall, characteristic equation. Then we have to find eigenvalues, then eigenvectors for the process. What is Hermitian? As Hermitian, we says A equals to A transpose. In unitary, we have seen U transpose equals to U transpose U. Yes. So overall, we have studied